Hello, everybody, and welcome to We Measure the World, a podcast produced by scientists for scientists.
Even if tomorrow morning we stopped burning fossil fuels, which is unthinkable, if from tomorrow morning there's not a single molecule of CO2 from fossil fuels going into the atmosphere, the climate will not reverse quickly because we reach already over 400 ppm in volume in the atmosphere. So in any case, we're going to have to adapt and mitigate what we already did so far. So understanding the water budget, the soil water budget, plant dynamics, cropping systems, it's key. I mean, we are going to be between 9 and 10 billion people, they estimate. If you look at FAO, they have a certain number, the United Nations has another number, but the estimation is like by 2050 will be probably around 9 billion people, if not more, on the planet. So we need to feed the 9 billion people in a changing climate. These are challenging topics.
That's a small taste of what we have in store for you today. We Measure the World explores interesting environmental research trends, solutions to research issues, and tools to better understand the entire soil-plant-atmosphere continuum. Stay current on applied environmental research, measurement methods, and more. Thanks for joining us.
Today's guest is a soil physics expert, Dr. Marco Battelli. Marco received his bachelor's degree in agricultural sciences from the University of Bologna in Italy and his master's and PhD in soil physics from Washington State University in Pullman. He spent a year as a postdoc in the physics department at the University of Heidelberg and now teaches courses in soil physics, hydrological modeling, philosophy of science and scientific methods at the University of Bologna. Marco is a referee for the National Science Foundation and also serves as a reviewer for international journals. He is the author of 2 books and the co-author of multiple book chapters, journal papers, and has over 70 papers in conference proceedings. And to top that off, he is also a signed jazz guitarist and has released 3 albums. Marco, thanks so much for being here. I'm really excited to talk with you. Can you start off by telling us how you got into your field and also how you got into jazz guitar?
Oh, yeah, okay. Well, when I was a teenager, my mother took me to a trip to Egypt. My mother was a professor of mathematics, and when she retired, she became a travel guide because she loved to travel the world, and so she went all over the planet, and she took me to Egypt. And I remember in Thebe, which is this beautiful ancient city on the Nile River, we drove into the desert and there was this botanical garden within a greenhouse, very big, kept by a British man. And he was established by the British government a couple of centuries before. And it was just unbelievable to see that, of course, there was water there, there was a deep well. So in the middle of the desert, there was this incredible botanical garden with an enormous variety of species. And so I came back from that trip deciding to study plants and soil and the environment. So I finished high school, and then I enrolled at the University of Bologna in the Department of Agriculture. And that's where really the initial motivation. Then along the way, originally I wanted to study tropical crops because of that very trip. But then along the way, I met this wonderful professor, Professor Luigi Cavazza, who actually recently passed away, who was teaching soil and environmental physics. And when I took his class, I found that was the subject I wanted to study. And so that's the motivation for science. Okay. For guitar, my brother is a professional musician and composer. He actually wrote songs with Vasco Rossi. I don't know if there is an Italian listening to this podcast, but if there are Italians listening, Vasco Rossi is our biggest pop star in Italy. Oh, wow. Really number one. So he's older than me. My brother is 6 years older than me. And so he gave me a guitar when I was 12. And then the love for music has been running in the family. My grandfather was a musician, so it's been always running in our family. But I didn't make it a career. I decided
a hobby.
Just a hobby. Yeah, just a passion.
Very successful
just
hobby,
a passion,
apparently.
Yes.
Yeah, so we're super excited to have you so we can kind of have this discussion of some of your more recent projects that you've been a part of.
The largest project is in Antarctica. So Italy and France have an experimental station. It's called Concordia. This is an important station that has been going for a long time. In the summer, there are up to 200 scientists who work in that station. They do research in a variety of areas related to ice and Antarctica and climate. Our project is dedicated to the measurement of the electric properties of the Antarctic sheet, basically.
Okay.
The reason is because the thickness of the sheet is determined by a variety of methods. They are measured based on gravity, they are measured based on GPS, but an important method is by satellites. With radar and microwaves satellites that are sending signals, if they are active satellites, if they are passive, they're just receiving the signal. And the time the signal takes to cross the ice help us to understand the thickness of the ice.
So when you say the sheet, you're talking about the ice cover.
Yes. So under Antarctica, we have the rock and it's very thick. It's a very thick amount of ice. And then we need to know how much ice we are losing, if we are losing, and we know we are losing it.
Right.
There's been some debate for a few years, but now we know, unfortunately, we are losing a large amount of ice in Antarctica as well. So we need to quantify and understanding the process related to climate change. I, together with many thousand other scientists, believe this is the most serious issue we are facing as human species this century. It is an incredibly serious problem. We studied also in the Alps. I will get to that topic later. But what our project is dedicated to is to collect ice cores, measure the dielectric properties of ice cores to be able to improve our models for the satellites. We already published a paper recently in called Regions, Science and Technology, in which we are showing the data and we developed a model that allows to have this information for remote sensing.
So some of that work then is ground truthing.
Yes, it's mostly done in situ. So we go there and we collect ice cores. And we also bring the ice cores back to Florence. So they go on boats and they go all over the planet.
You have to keep them frozen.
Yeah, of course. We need to keep them at the same temperature at which they are collected. And then when they arrive in Florence, in our cold room laboratory, we measure additional properties, mostly chemical properties that we have more difficulty measuring in situ.
Okay.
Because there are some ions that are present in the ice that affects the dielectric properties, in particular the imaginary part.
Okay.
And then we do a lot of modeling. Clearly, after having collected the data, we have these dielectric models, the electromagnetic models to characterize the ice. So that's been my most important in terms of time and money and involvement. And we also study ice in the Alps. This is a very recent project that I'm going to start in September. And again, is to try to characterize snow melting and ice melting, because also our glaciers in the Italian Alps are losing a large amount of ice and snow every year. And so this is very serious because the entire Po Valley in North Italy, is affected. The water budget of an area where millions and millions of people is determined by the recharges of groundwater and rivers, so both surface and underground water, because of snow melting.
Okay.
So if instead of having snow slowly melting into the soil and recharging the groundwater, we have just precipitation as rain, is a completely different ball game in terms of the water budget. And so this will affect availability of water for agriculture and for cities.
Does that affect water quality as well?
Yeah, certainly. certainly, because you have more runoff
with the rain as opposed to the snow.
Movement of sediments and pollutants or nutrients. So it's very different.
Right.
I mean, a water budget driven by snow melt or driven by rain.
How does glacial runoff play into something like that compared to like a glacier melting versus active new snowfall or precipitation?
Well, glaciers formed because of accumulation of snow that under a certain temperature level, below zero, over the geological eras, obviously over a long period of time, became a permanent glacier. So when you have a decrease in snow melting, you are not accumulating new snow into the glacier. And if you have a higher temperature, you are melting. There are so many images and pictures. But I was last year, I also like to climb mountains as one of probably my third passion. I like to climb mountains. So last year I went to the summit of the Marmolada, which is the only glacier we have in the Dolomites. And there was a hole that they made at I think it was 1895. The hole was made in the rock to be able to hide into the rock from the glacier. So they were walking from the glacier into this hole, into this cave. Now that cave is 95 meters above the current level of the glacier. It means that from approximately, let's say, 1890, so 130 years ago, something like that, we lost a thickness of about 90 meters of glacier. When you see that, it's bang, it's right in your face. You realized how much ice we are losing. And there was a paper, the EGU, the European Geophysical Union, that we have in Wien every year, that there was a paper that estimated that by the end of this century, all the glaciers in the Alps will probably be gone. Now, of course, I hope that paper was wrong. But if we don't change direction, it's going to be incredibly problematic issue. Most of my research now is directly or indirectly related to this. Even another project we have is to study landslides and the water budget in vineyards in Italy or in different agricultural settings. But that also related to climate change, because in Italy, when I was a student in the College of Agriculture, we knew that we did not irrigate grapevines for wine or for eating grapes. It was not an irrigated crop. Today, it is an irrigated crop, meaning that many farmers realize that if they don't have a drip irrigation system, some seasons, because of the lack of water, of the high temperature, they cannot get enough yield, or the wine quality is very bad, or there is too much sugar, therefore too much alcohol. So it became an irrigated crop now in Italy, even in the north. Between when I was a student, now I'm 54, so in over 30 years. So cropping systems are changing, and that's why I think the devices you develop at Meter, we use them all the time because we really like your devices, are very reliable, but they're very important. They will be more and more important because we need to monitor, and at this point we cannot really completely reverse it. Right? Even if tomorrow morning we stopped burning fossil fuels, which is unthinkable, if from tomorrow morning there's not a single molecule of CO2 from fossil fuels going into the atmosphere, the climate will not reverse quickly because we reach already over 400 ppm in volume in the atmosphere. So in any case, we're going to have to adapt and mitigate what we already did so far. So understanding the water budget, the soil water budget, plant dynamics, cropping systems, it's key. I mean, we are going to be between 9 and 10 billion people, they estimate. If you look at FAO, they have a certain number, the United Nations has another number, but the estimation is like by 2050 will be probably around 9 billion people, if not more, on the planet. So we need to feed 9 billion people in a changing climate. These are challenging topics.
With your discussion and interest in climate change and how it's affecting agriculture and other aspects of our daily lives, does this play into your projects as well? You've worked on some projects with levees in the Po River or in shallow landslides and those kinds of things. Are those related to your...
I mean, it's not only related to climate change. Floods existed before, and there were floods 300 years ago. But probably with changing precipitation patterns and the frequency of certain extreme events, this will become even more an issue. So the protection of river levees, indeed, and landslides are driven by the fact that the material saturates, soil saturates, and then you reach a certain threshold for the mechanical properties, and then the landslides can occur. There is, of course, quite a bit of physics and mathematics behind it, but really the water... I like to say water potential better than water content, because really the variable we need to know to understand the process of landslides is the water potential.
For those listening who maybe aren't familiar with the term water potential, can you describe how that compares to just basic water content?
Sure. Water potential is the energy state of water in a system with respect to a level, with a reference level that we assign to have a zero water potential. So if we imagine to take a bucket of water, we put it on this table. So from the gravitational standpoint, we can decide that this table is at level 0. But commonly, we choose the ground surface as our level 0. So if I move this bucket of water up or down, I change its gravitational potential. Now, if this water is completely free of ions, so it's pure water, there is no forces exerted on this water by the fact that there are bindings with the ions. So the osmotic potential is 0. Now, if I take this water and I put it into a vase with soil, then the water is binded by capillary forces and absorptive forces on the surface of the soil. So in that case, the water is not free to move as it was before. So that's called the metric potential. So the water potential is basically the energy state of water in a given system. It can be a soil, it can be a plant, it can be a food, it can be a cracker or a piece of bread. So with respect to a reference level. And so the energy state determines the water movement and the rate of water movement, for instance, within the soil. So water moves in the soil because there is a difference in water potential. So it's a difference in the energy state.
So that's why it's much more informative than just knowing how much water is there, because it tells you something about the energy state of the water and where that water might go in the future.
Absolutely, yes. Clearly, the two properties are related with what is called the water retention curve that puts in relation the metric potential and the water content. But really, what the driving force for movement, it's the potential. But even in the vapor phase, I mean, the water moves from the soil through the plants toward the atmosphere because there is a gradient in energy. This applies also to water vapor.
So I know that you've done a little bit of work looking at the best way to actually measure and understand metric potential, and you've compared pressure plates and other methods. Can you talk a little bit about that work?
Yes. Pressure plates is a classic technique that I think it was developed by Richards, who is a very famous scientist in our field. That's why they're called Richards plates. So I guess that's why he developed those. And the way they work, basically you put a sample into a container, then you apply an external pressure, for instance with a compressor, and then when you think that you reach a certain equilibrium, let's say a 1 bar, then you see when water stops dripping out from that container, it means that the water is at equilibrium with that pressure. And then you take out the sample and you measure how much water there is in that sample. And so you create a relationship between a value of metric potential and a value of water content. By repeating this measurement at different pressure, you develop a water retention curve.
Because every different type of soil has a different relationship.
Yes. A sandy soil has a different water retention with respect to a clay soil, so a silty loam and so forth. But also you have a different level of water content, a different level of water potential. The lower the water potential, so the more negative, the less amount of water you have. So that sometimes is expressed as an absolute value, but if you think it as a minus sign,
right.
So the amount of energy that you need to apply to bring it back to zero, then the drier the soil, the lower is the level. So, but we found out already, I think the first paper was over 10 years ago, that when the soil gets very dry, the soil does not really reach equilibrium. Okay. Even if you leave it in the plate for many, many days or even months. Mm-hmm. The reason is that the hydraulic conductivity becomes so small when the soil is so dry, it's very difficult for the sample to reach equilibrium and to be able to really identify the exact value of water potential with respect to the water content that you have in there. So in practice, you don't see the water that should come out at that level of water potential because the hydraulic conductivity is too small. So that technique provides wrong data. Below, I think it was about 50 joule per kilograms. We found out that, so it's 50 kilopascal.
Which
becomes
for people who aren't familiar with that scale, that's right in that plant available range for water, right?
A little bit below.
A little bit drier.
Because usually plant available water, it is because it is right there. Plant available water is between field capacity, right, which is minus 30, let's say, for a fine soil, to what they call wilting point, which I think is another number that doesn't have much sense to me. The wilting point, and they will tell you why later. But the plant available water is in that range. So it's in the upper part of the plant available water. The soil is still fairly wet at 50 joule per kilogram. So I think there are many wrong data in databases. and then we found out that using dew point methods, for instance, methods based on equilibrium of the vapor phase, provides way more accurate value in that dry part. Let's say, it's not that dry, but below that value. Okay. So we first published a couple of papers showing the not reliability of these methods, and then we compare it with other methods that are more reliable. There is techniques in our field that, in my opinion, needed to be abandoned. Yes, that's the way in every field, I mean, in medicine, in engineering, you use a technique for a century or two. Now, pressure plates is not that old. I think they're from the 40s. But I think it's time to change. We have better techniques.
What are the techniques that you choose to use that you think are the best options?
Well, for water retention, I really like the high prop by a meter is an evaporation methods that provides the water retention curve. What I like about it is that it also provides the hydraulic conductivity because it's based on inverse methods. It computes the hydraulic properties from fluxes and known water potential because you have two tensiometers, so you know the value of the water potential in 2 points. So I use that technique. I still use vapor pressure methods for in the lab. More and more in recent years, I like to get the water retention directly in the field. And because also you see phenomena like hysteresis, and that, you could do it also in the lab, but not really, because the evaporation methods, is a drying methods. So you just dry the soil, and so you see only the drying part of the curve. Right. While in the field, although it's a little bit more complicated to analyze the data, you see the different branches of hysteresis. And so I usually place a water content and a water potential measurement right there in the field. Because
then you can see the dynamics of rainfall and evaporation.
Exactly. Exactly. I see the dynamics directly in the field. I can build the water retention because clearly I can take a value of water potential and water content at the same time. Yeah, that's what I do more and more.
So earlier you had touched on working with river embankments on the Po River and also talking about those shallow landslides. Is that primarily using water potential, or are there other measurements that you're using for those projects?
Well, there are a series of measurements that geotechnical engineers do. So mechanical properties, resistance and friction angle. I want to say I'm not an expert in soil mechanics. I work with geotechnical engineers and they take care of that part. You can't do everything, at least for me. I couldn't do everything. So it's an area of soil physics that I'm probably not the most expert in it. But we work together well. I work with the geotechnical engineers who take care of soil mechanics. I take care of the hydrological measurements, modeling of soil water movement, and the water budget, so the contribution of plants and so forth. Mm-hmm. So they make a series of measurements for mechanical properties, and I make the measure for the hydrological properties. In terms of hydrological properties, yes, we measure water content, water potential, hydraulic conductivity is very important. They call it permeability. The geotechnical engineers call the water potential suction. Mm-hmm, mm-hmm. I've been trying to convince them to change name because in physics, it is a physical properties mm-hmm. and it's an energy state. But they keep calling it suction, which is fine. I'm just joking. Yeah. So we measure suction and we measure water potential and the water budget.
And so in working with those various measurements, and especially if you're dealing with slope stability or embankment stability or other things like that, are there any difficulties that you run across in making those measurements, or at least trying to interpret the data that you're coming across?
Well, the first difficulty we encounter was to reach depth that we usually don't reach in agriculture because the levees are very deep, So we built an instrument that I think meter than a patent that is now selling it. I have to say the idea was of Paolo Castiglione, just for reference. Basically, it is an installation device that allows to install the sensors. We went down 8 meters, if I remember correctly, but the paper is published. Mm-hmm. So the idea was, okay, you cannot dig a trench in a levee, otherwise the levee goes down, right? So the problem is to don't be invasive. Mm-hmm. And while in agriculture, the root zone, when you go down 1 meter, 2 meters, you're happy. And also often in agriculture, you can't dig a trench without making much damage to your field. In those conditions, you cannot do it. And so we drilled a borehole, and then we developed this device that is able to push the sensor inside. And there is also a little camera. So we could see if the sensor was properly installed into the soil. And that was very neat. I like it because we could get information really quite deep in
through the profile.
In the profile.
Yeah, we've had a lot of folks who have really enjoyed using the borehole installation tool because it is much less invasive.
And it's much less labor too. You don't have to dig so much.
And it's less expensive also because if you have to dig a trench, you have to get a specific machine that costs some money. So that was we worked together. I mean, we did our contribution, but I think the mechanical part really was Paolo came out with that idea of putting the leverage. And that worked well. That was one challenge. The other challenge that we are facing today is spatial variability. I mean, not today, it's been known for decades, is that even across the river, the properties changes so much, especially in Italy, that is a very old country. I mean, those levees were developed over centuries. And so who knows what they used at the time? Of course, you can probe and collect sample and understand what material they use, but they are very variable. So that's another issue. We need to work on methods that get information on the spatial variability. That's why I've been working on GPR, so geophysical methods. Now I'm working, but I've been just using a methodology that is developed by Professor Mantovani in Ferrara, who developed a gamma ray proximal spectroscopy with gamma ray that allows to get information on water content over larger areas. Again, it is his field. He's working on it. I don't have a gamma ray in my lab. I mean, I don't work on it, but I started to use it, and I found it very promising as a method. So the next challenge for us is to try to incorporate in our models this natural or human-made spatial variability, both in natural conditions or in man-made structures.
You've kind of been talking a bit about climate change, and we've reached this point of no return in a way. And so how do you keep from getting really discouraged and deal with maybe some of those negative emotions that your research brings up?
Well, I have faith in humans. So I think we will overcome this. We will pay a price. We are already paying a price for what we did to the planet, but it was part of our evolution. So, I'm not that kind of person who think we could go back to, using horses to move around. So fossil fuels was a part of our history. We found out that we could use that energy to improve, to have better lives. I mean, if you think of the lifespan of humans, like 200 years ago, when Mozart was alive, I think their average, length of a lifetime was about 40 years. Now is about 80. And so we improved on many, many aspects on the human rights, on technology, society. So fossil fuels were a chapter of our history as humans. We need to move into a different chapter, and I think we have the capabilities to do it. We need to build awareness. This is a global problem. It is an issue that involves all of us from everywhere. United States, China, Europe, India, Australia, Russia, the entire planet is involved because these are processes that are not limited. Now you're having a lot of fires here in the Northwest, and then in other areas there are floods. We need to think globally like an astronaut will do. If you think those astronauts who stay in the International Space Station, they look at Earth and they see it as one thing, they see it in our Mother Earth. That's what we should do. We should think more globally, be less selfish. So think about the planet as one thing, and then I think we'll be able to overcome this problem, and we will have learned. Because all the sciences that we are doing now will be science that will be with us. And I have 2 children, so I like to leave them a planet that is still livable. I definitely feel emotional, as I said. I love the mountains because my father loved the mountain himself. I was 16, 15 when he took me to those peaks in the Alps. And so now when I go back, seeing the landscape changing so much, it is emotional to me. I see the impact that we have on the planet. But for me, it's a motivation. And I tell the same to my children because it's something we all have to do. Where we have democracies, we can vote. We can buy an electric car. We can install solar panels on our roofs. We can use less water. We can eat differently. There are a long list of things that as individual we can already do. I took a cab coming back from the Alps, going back to Bologna in my last field trip, and the taxi driver had an electric car. Oh, wow. So I spent the entire time interviewing him. I learned a lot of great stuff. He has a charging station in his garage. At night, he has a fixed price of 120 euros a month, regardless how much energy he draws. So it's much less expensive than gas for him. He goes to sleep. With one charge, he does 450 kilometers, which I think is about 300 miles. So it's perfectly enough for his work as a taxi driver. And so it works.
Right.
Obviously, that energy must be produced without burning
Fossil
fossil
fuels.
fuels. Otherwise, it doesn't make much sense. But we have the technology to do it. So a long answer for a short question. But yes, I do get emotional, but I'm optimistic. I don't think we will extinct. Sometimes you read the extinction of the human species, stuff like that. I don't believe that. We will have to adapt to a different climate, but we'll be able to do it.
Right. And the more you learn about climate change, the more we know about how to mitigate it and make improvements.
Yeah, we need to understand it, how to mitigate it. Think about Venice, but even Miami. There are cities where they are already building structures to contain the water because of the rising sea level. And these are big projects, they're not small things. So we need to be able to quantify these changes in an accurate way.
I think one of the difficulties is that a lot of times it's human nature to be very myopic and self-centered and not proactive because they don't really see the effects that it has on them right now.
Exactly.
Or in the future.
You got the right point. And allow me this comparison. Look at COVID. COVID has been a very serious thing, so I don't want to be misunderstood. I understand today we're about 4 million people died globally of COVID. So it's not a joke. So I want to make this clear. But if we reacted to climate change and for the seriousness of the topic, the same way we reacted to COVID, we could do an enormous amount of things. Mm-hmm. The reason is that it's easy for me and for you to understand the risk of ending up in an hospital with tubes in your nose to breathe is a very palpable, immediate fear. And with that fear, we stop the world. You remember the images of New York, Rome, and Paris completely empty is out of a movie. Mm-hmm. We were able to stop the planet. Flights, people were not flying because of a virus that killed 4 million people. And the reason is that it was easy to convince people of this threat. Now, climate change, if we don't act, will be way more serious than COVID. By orders of magnitude more serious than COVID. But the reason we cannot convince people to act as strongly is because it's a challenge that we don't really perceive. And so the problem with climate change is, as you said, you exactly nailed the point here. I mean, you got it. We need to make people understand about the seriousness of this issue, even if they don't perceive it immediately as a risk for their health. And we have the power to do it.
Are you working on any current music projects?
Yeah, I'm recording my fourth album.
Okay.
Fourth album, yes.
Mm-hmm. Awesome.
Yes. So I think I will have a new album next year.
Oh, exciting.
That's great. That's great. We'll look forward to it.
Well, I think our time is up. So thank you so much again, Dr. Bittelli, for taking the time today to talk with us about your research and music and life advice and all that fun stuff.
Well, I want to add something because I know this podcast is made here at Meter, and I really enjoyed working with the people here, and I've been working with them for a long time now, and it's really great, beautiful to collaborate. Very open-minded people, great serious scientists. Galen Campbell was my major professor, and then all the people here, Colin and all the family. So yeah, I've been lucky to meet such smart and generous and good people. So I'm happy to be here today to speak.
We're grateful that you were able to stop by and
absolutely
chat with us. We appreciate your insight and all the work that you've been doing.
And if you listeners have any questions about this topic for us or for Dr. Bittelli, you can always feel free to contact us at metergroup.com, or you can send us a tweet at meter_ENV, or you can reach out to me at HLPlants. And you can also view the full transcript from today in the podcast description.
That's all for now. Stay safe, and we'll catch you next time on We Measure the World.